Good morning, ladies and gentlemen, and welcome, and thank you for filling up the hall. I think we are in for a very interesting morning. I think we've all wanted to know for a long time what artificial intelligence is all about. It is my pleasure to welcome Professor Jonathan Schock this morning. He is an associate professor of mathematics at the University of Cape Town and a director of the Neuroscience Institute. Professor, thank you very much for addressing us this morning, and please go ahead when you're ready.
Where do we want to begin with a talk like this? We could start in the mid-19th century with Ada Lovelace, who was really the first computer programmer. So Charles Babbage had invented the difference engine, although it hadn't been built. It was a theoretical computer at the time. And Ada Lovelace showed how one could program such a computer. So she was really the first first software engineer, the first computer programmer. We could start with the Mechanical Turk, this image in the middle here, which was a chess-playing automaton which toured Europe for somewhere around a century and would play against kings and emperors and would almost always beat them. And this was incredible. You know, we now have chess computers which can beat humans, but this was a couple of hundred years back now. And so the fact that they were able to have this automaton that could beat people was pretty amazing. The rub here is that it actually turned out that there was somebody sitting inside the box moving the pieces, and it wasn't really a mechanical Turk at all. It was a human sitting in there. Or we could start with Alan Turing, who really brought us the sort of modern ideas of the theory of computation. We really wouldn't be where we are today in terms of artificial intelligence, information theory, or computer science if it weren't for Alan Turing. But in fact, I'm going to start at a different place. I'm going to start back in around 1890 in Spain, and the neuroscientist Santiago Ramon y Cajal, who drew these incredible pictures from microscope slices of human brains. So what we see here on the right are his images, which were of the different types of neurons that he found in the brain. And we understood a little bit before about the neurons, but this really gave us the first insight into how these things were connected, the types of neurons that were there. And what we have to remember is that everything that you are experiencing at the moment, all of the thoughts, all the feelings, it all comes about because of the electrochemical processes going on in the neurons in your brain. This sort of network of connections from one neuron to the next through the synapses, all of the information processing, all of the feelings and thoughts that you have happen through these neurons. And what we're going to see is how the understanding of the neurons led to the understanding of a sort of abstracted computational version of the neurons, which then gave rise to what we call neural networks, artificial neural networks, which are really the cornerstone of today's modern AI systems. So we can take these neurons and we can sort of draw a cartoon of them. And what we have here is two neurons connected together. So we have dendrites, which are sort of the incoming lines here, and then there's an axon which goes out and it connects to the next neuron via a synapse. Can you see my mouse when I'm moving the mouse around here?
Yes, yes.
Yeah, perfect. And so in fact, what happens is that you have incoming neurons into one neuron, and the signals, the electrochemical signals from those, add up in the nucleus. And if there's enough of a buildup, there's what's called an action potential, and there's a signal which gets sent down the axon. And this signal, you can actually measure it. You can take a neuron and you can do what's called a patch clamp experiment, and you can actually measure the voltage change across the neuron. So these things have this sort of binary, either they're firing or they're not. And when they fire very quickly. So you see this is about a millisecond, thousandth of a second that it takes for a neuron to fire down the axon, and then the next neuron is affected by that. Okay, so we have this sort of cartoon drawing here of the neuron, which is something like what's happening in the brain. Now we're going to change tack completely, and we go back to the middle of the 20th century, the beginning of the 20th century, and Alfred North Whitehead and Bertrand Russell, who were mathematicians. Bertrand Russell, of course, a philosopher as well, logicians. And what they were trying to do was to take mathematics and put it on a really firm footing, asking the question, what are the simplest ingredients that we can start with? Can we start with, even simpler than, for instance, addition, and build up to addition, prove everything from the ground up? And they wrote this three-volume text, the Principia Mathematica, around 1,500 pages. And around 400 pages in, they get to this this section here, where we see from this proposition it will follow when arithmetical addition has been defined, that 1 + 1 = 2. So we can see that it took them almost 400 pages to prove that 1 + 1 = 2. And don't worry if you don't understand all of this. This is very, very formal mathematics, but essentially what they were able to do was to build mathematics from the ground up through this very, very logical structure. Okay, why does this matter? Well, now we go forward a bit to 1935, and Walter Pitts is in Detroit, Michigan, and he's being chased down the road by a bunch of hooligans. And he ducks into a library to get out of the way of them, and he manages to. He escapes them, and he goes to the back of the library, and he's browsing through the books, and he finds a book, and the book he finds is the Principia Mathematica. And he starts to read it, and he's enthralled in a way that I think most of us, if we looked at the Principia Mathematica, would not be, but somehow he's absolutely taken in by it. In fact, he manages to hide out, and the librarians close the library. They don't see him, and he hides out in there for 3 days reading this book, really digesting it in great detail. He writes to Bertrand Russell after this and says, I read your book, the Principia Mathematica. It was amazing. It's really, I've had some profound insights from this book. He asks some questions, makes some suggestions, and Bertrand Russell writes back and says, this is amazing. You've clearly understood the depth of this work. Would you like to come and be a graduate student with me? There's a problem with this, though, and the problem with this is that at the time, Walter Pitts is 12 years old. Just completely remarkable. This is somebody who I think we really should know a lot more about. Unfortunately, he led a pretty difficult life and died in his 40s of cirrhosis. He'd been an alcoholic. He'd really come from a broken home. But at 12 years old, this guy is a genius. He's understood this unbelievably complex book, and been able to engage with one of the greatest philosophers and mathematicians of the 20th century about the topic. A little while later, I think around 4 or 5 years later, Bertrand Russell is in Chicago, and Walter Pitts goes to Chicago to see him talk, and he meets Jerome Letvin. And Jerome Letvin here on the left is he's a medical student, but he's into music and art and theater, and Walter Pitts is into mathematics, logic, and really trying to understand the deepest truths of the universe through logic. There are various other things that happen in very much a sort of goodwill hunting way. Walter Pitts ends up meeting another logician at the University of Chicago, Rudolf Carnap. He goes to one of his lectures and then goes along afterwards to Rudolf's office and says, I've read your book and I think there are some mistakes in it, and it turns out he's right. And then he leaves, and Rudolf Carnap tries to find this this genius, and can't, because he's not actually a student there. He eventually, after months and months, manages to track him down and gets him a menial job within the university as a janitor, and starts talking to him, and they form a bond. At this time, Walter Pitts is actually homeless, but has become good friends with Jerome Letvin, who is now studying under Warren McCulloch, who's a neuroscientist. Warren McCulloch and his wife take in Jerome Letvin and Walter Pitts into their home and say, you can stay here. And here a really important relationship is born. And that relationship is between Walter Pitts, this logician, this mathematician, and Warren McCulloch, this neuroscientist. And they start talking in the evenings about the brain. And they realize that, whereas previously people had thought of the brain as, this just wet piece of sort of hardware in our heads that somehow gave rise to the subjective experience that we have. They say, well, what if we were to take these ideas of the neuron that came about at the end of the 19th century and see if we could write down a mathematical model of the neuron, a very, very simple one. The fact that the neuron seems to take in these signals, do some sort of arithmetic with the signals, and then give you an output. They reason that actually you can come up with a mathematical model of the neuron. And this is what they do. They come up with a paper which is called A Logical Calculus of the Ideas Immanent in Nervous Activity. And papers really don't have the sorts of titles that they used to have. This, I think, is a rather glorious title. And this is the first paper which really tries to put into a mathematical form what is happening in the neuron. And they say here, because of the all or none character of nervous activity, neural events and the relations among them can be treated by means of propositional logic, sort of a very basic form of mathematics. Unfortunately, this paper, so we have here Pitt and McCulloch on the left, this paper is largely ignored by the logicians because it's a bit too biological, and it's ignored by the biologists because it's a bit too mathematical. It also turns out that it's really a bit too much of a simplification. So a little while later, they write another paper, which is called What the Frog's Eye Tells the Frog's Brain. And this is actually together with Jerome Letvin. And this is a sort of slightly more advanced version of these ideas. But really what they've done here is that they've formalized a sort of abstract version of the neuron and said the neuron is doing some sort of computation. This is very important. Okay, now we move on. We move on to 1958, and Frank Rosenblatt invents what he calls the perceptron. So I'll explain this diagram in a moment, but what I want you to think about to begin with is what happens when you see the letter X written on a piece of paper? What's happening? So the photons, the light comes into your eyes, is focused and goes through to the retinal cells in the back of your eyes, the retinal ganglion cells. Those get passed through via the optic nerve to the back of the head, to the visual cortex, and is passed through a series of neurons. And each neuron may be connected to many, many other neurons. And there is this sort of mathematics. There's a computation that goes on. And eventually it gets to a part of the brain where there is that sort of conscious, okay, I've just seen an X, or, if it's a Y, I've just seen a Y. But what's really happening is there is that the signals are being integrated in some way across your visual field, and there is some recognition in your head, okay, that's an X. So what Frank Rosenblatt did was to say, well, can we do this in a purely sort of mechanical and electronic way? So what he had was a picture, for instance, of an X, and essentially a load of digital cameras that were taking an image of this, and each one took a little patch of the X, and we see here that there are regions of light and dark, or black and red in this case. And it sends through the signals from this through to some complex set of wiring, where the complex set of wiring is adding up, combining the features. You can think of these as being, let's say, zero here and one here, a sort of binary representation of the pixels, that it's the equivalent of the pixels in the image. And somehow there is some calculation that happens that when the wiring is right, it outputs that it has seen an X or it's seen a Y. So the details of this don't matter too much, but what's important here is that with the right wiring, with the right way of adding together the particular pixels, it can pick up features from this X in exactly the same way that your brain does, or at least a very similar way to the way that your brain does. Your brain is just taking this input signal into your eyes. The signals are coming together at neurons, they're going out to other neurons, and somehow there's a calculation which triggers a neuron in the end, which is the, aha, I've just seen an X neuron. It's a little bit of a sort of cartoon version, but that's essentially what's happening. Okay. So, of course, if I just do random wiring here, then the output signal, well, it's not going to have anything to do with whether or not that's an X or a Y. In the same way that if I scrambled your brain and I showed you an X, there wouldn't be, a part of your brain that is able to recognize an X anymore. But if I wire your brain up just right, then whenever you see an X, your brain is going to say, okay, that's an X. And whenever you see a Y, your brain is going to say, okay, I've just seen a Y. Okay. But the wiring is really important. So what Frank Rosenblatt did was to essentially take this wiring and more or less by hand change it so that whenever it saw a picture of an X, it was likely to say, this is an X. And whenever it saw a picture of a Y, it output, this is a Y. This was a rather complicated job. So this is Frank Rosenblatt with his perceptron, and this is the wiring going on here. It's a pretty complex piece of machinery with essentially 400 receptors, the equivalent of the retinal cells. And the wiring here is what he could change. So he could alter the wiring in the center here, and they would output, depending on the letter it saw or the number it saw, it would say, okay, this is a 1, or this is a 2, or this is a 3, et cetera, et cetera. Okay? The important point here is that he had to do this by hand, more or less. Of course, as you learn something, as you learn to recognize X's and Y's when you learn to read, or 1s, 2s, and 3s when you learn to read, you're not having to do the wiring in your head by hand. It's all happening through essentially trial and error learning. Okay? What's happening there is that whenever there's an error, there's going to be an update in your brain which says, you got it wrong. What do I need to do differently next time? And essentially, what that's doing is changing the wiring in your brain. And here, of course, there are more layers in the visual cortex than just the one here, but it's changing the wiring so that next time you see a picture which is an X, you are able to recognize. Now, at the time, the New York Times said that the embryo of an electronic computer that the Navy, this was funded by the Navy, expects will be able to walk, talk, see, write, reproduce itself, and be conscious of its existence. So that was maybe a little preemptive. This thing could tell the difference between handwritten digits. So it was trained on handwritten digits. And what I mean by trained here is that you pass in an image, it either gets it right or it gets it wrong. And if it gets it wrong, then you change the wiring slightly so that it's more likely to get it right the next time. So this thing here, the perceptron, is essentially the individual unit which makes up the neural networks that we have today, which correspond to the ChatGPTs of this world. So what's going on? So we can actually look at a particular data set, which is often used for training, something like the MNIST data set. And what we have here are handwritten digits. And so what you want is to have this sort of network which is able to tell the difference between all the different digits. And we can take a particular 5, and when you zoom in on it, it's just a pixelated image here where there are different shades of dark and light, where the dark corresponds to a numerical value of 0, and the light corresponds to a numerical value of, let's say, 255, the way it's encoded in binary. And so I can take an image and I can transfer it into numbers. Okay, so this is a 0, this is a 255, this is a 123 because it's somewhere in between on the grayscale spectrum. And so I can take this image and I can transfer it into individual numbers, the pixel value. So this is important because, of course, computers, well, they use numbers. They work in fact in binary, but the point is that a computer doesn't know anything about a raw image in the way that we see an image. Okay, you have to turn it into what's called a matrix of numbers or convert it into a list of numbers. So you can think about taking this and it's just going to end up, this image here corresponds to 0, 0, 0, 0, 0, et cetera, 253, et cetera, et cetera. And so I can take an image and I can convert it to a long list of numbers, and then I can take those numbers and I can pass them into a computer, and with something like this, I can then, if the units in the middle here are right, I can train it to get the correct answer each time by somehow appropriately changing these units in the middle. Okay. So I just want to go through a sort of very simple example of this, and this is a kind of a really a much more simplified case. But we can ask, what's really happening with the perceptron, and what's actually happening here? We can think of this way. So let's say we have a classification task. Let's say we have a data set, maybe age and blood pressure, maybe comorbidity, vaccination status, previous infections, and maybe something about an outcome after COVID. And we want to be able to make predictions. A new person comes into the clinic, and we want to make a prediction. Are they likely to have a severe or a less severe infection? Okay, what's the outcome likely to be? And we can think about plotting this data. And I've just made this data up, but here we have age, and here we have blood pressure, and maybe those who are younger, those who have lower blood pressure, maybe they have in general, a better outcome, and higher age, higher blood pressure, the outcome is less likely to be as positive. And so one can see here that there's kind of there's a decision boundary in between. So we can think about putting a decision boundary in here, that when a new person comes into the clinic and they're here, this is their age and this is their blood pressure, we can make a prediction as to how, whether they're likely to need care. Okay. So don't worry about the maths here. I'm going to go through in a little detail, but not too much. It's not too important. What we can imagine here is that I pass in the age, which is a number, and I pass in the blood pressure, which is a number. And maybe there's some other number here. And I just output from this some mathematical combination between them. In particular, there's a W1, which corresponds to a weight here. It's like a synaptic strength in your brain, and a W2. And the output of this, if this output is greater than 0, then predict a 1. Maybe that's a positive response. And else predict a 0. Maybe that's a negative response. And depending on the value of this W1 and W2, different ages and blood pressures are going to be predicted to have good or bad outcomes. So if I take some random value of B and W1 and W2, then what that actually corresponds to is some decision boundary, some line here. And we can see that that's a terrible decision boundary. That doesn't correspond to this data at all. In fact, we see that there's a large error here in our predictions. If we use this to make predictions, well, most of the predictions would be wrong. A lot of them would be wrong. This one here, the lower error one here, this would correspond to, well, a slightly lower error than this really terrible one. And this corresponds to changing the values of this W1 and W2, which correspond to the synapses in your brain. Whereas this one is really the optimal error, which is the optimal value of W1 and W2. So what we can say here is that as we change the weights, the synaptic strengths, the prediction from this little module here is going to be better or worse. i.e. there's going to be more or less error in our prediction. So we can actually plot the error. And this is just a cartoon. But if I were to say, I want to know, how high the error is going to be, well, this line here, that's a terrible decision boundary. It gets lots of things wrong. Whereas the green one here, that's a really good decision boundary. So we can say that this one here, we can actually calculate it, and the error here is going to be very high, and here the error here is going to be very low. And the difference between the lines are really the difference between those parameters, W1 and W2. And as I change them, I get more or less error. And my aim is to move around in this space of parameters, changing the synapses in your brain, or the parameters in the perceptron, until I get the lowest possible error, which corresponds to making the predictions as accurate as possible. And then I can use these values, which correspond to this line, to make future predictions. So in fact, this thing here, the perceptron, which was invented by Rosenblatt, as we saw, you can actually have lots and lots of inputs. This should be an X2 here. So I might have a load of inputs from X1, X2, up to Xn, and there's a load of weights here. And this can be this is now what's called some linear combination of the inputs. And I can use this to make predictions on data. Maybe I could make a prediction on the price of houses based on the features of the house. So Marvin Minsky and Seymour Papert wrote a book called Perceptrons, which actually showed that there were some limitations in the types of predictions that this sort of algorithm could do. There were certain things that you couldn't make predictions on. In particular, let's say you have data that looks like this, where maybe it's some prediction where there's a region in the middle where you have a bad outcome, and stuff around the outside, well, you have a good outcome. So if you just have a linear decision boundary, a straight line, there's no way that you can draw a line here which separates the green and the red. You need something like a circular decision boundary in this case. it actually turns out that you can take these individual perceptrons and you can put them together in particular ways that do allow you to have this sort of nonlinear decision boundary. So it turns out that, in fact, you are able to do much more complicated things. You can make predictions about data when you put together the perceptron, this thing that Frank Rosenblatt put together a long, long time ago, back in the 1950s. You can make predictions about very complex things. For instance, I can take pictures of cats and dogs. So each picture here corresponds to a set of pixels where the pixels have particular values corresponding to their red and their green and their blue amounts in each pixel. And I can think that I can then take that and I can write out all those red, green, blue values of the whole thing. And it might be a million numbers, maybe for a 1 megabyte image, somewhere on the order of a million numbers. And this picture of a cat lived just at some point in this really high dimensional space. I've just drawn it here as a 3-dimensional space. And this cat here lives here, and this cat here lives over here, or this picture of a cat. And this picture of a dog lives here, this one lives here, and this one lives here. The job of our algorithm is to say, how can we slice this space so that on one side of the slice live cats, and on one side of the slice live dogs? Really what's happening in your brain, more or less, is that the calculations that are going on to classify cats and dogs in your heads are saying, what are the features that give rise to a prediction cat, and what are the features that give rise to a prediction dog? So that now that I have this slice through the space, everything to one side I'm going to predict as a cat, and everything to the other side I can predict as a dog. But the question is, how do I find this slice? How do I find the right numbers? Well, what happens is I take an image of a dog and I pass through all the numbers into each of these nodes here through what's called a deep neural network now. This thing here is it's called the perceptron, and we put them together into this deep network, which now corresponds a lot more to the type of connections that you have in your visual cortex. There are multiple layers within your visual cortex, and it outputs a prediction cat. And of course, that's wrong. So what you want to do then is to take the error, the fact that this has incorrectly predicted that this is a cat, and you pass it back and you say, well, let's just tweak the weights, let's tweak the connections here a little bit so that we are more likely to predict that this images like this are a dog in the future. Of course, you don't want to do that by hand, as Frank Rosenblatt had to do. You want an automatic algorithm, and the way it happens is something called backpropagation by gradient descent. Details don't matter. But we are now able to train this connection of perceptrons, which we call a deep neural network. It's a network because it's this sort of connection of weights and inputs. It's neural because it's founded on the principles of the brain, and it's deep because there are multiple layers here. We see multiple layers in the middle from the input layer to the output layer. Okay? And this is what's called a deep neural network. It's just a collection of computational units that take in the numbers from an image, in this case, or like text, and output a prediction. And using particular algorithms, we can train this sort of neural network by automatically updating the parameters, the strengths of the connections, so that we are able to correctly predict whether something is an image of a cat or a dog, for instance. So, of course, you need a lot of data to do this because you need to be able to generalize. So, if I just showed you and you knew nothing about them, a single picture of a cat and a single picture of a dog, then if I showed you another picture of a dog, because, well, dogs are often quite different sorts of different looking animals, you might not recognize that that's actually a dog. So, of course, you need lots and lots of data, lots of images of cats and dogs to be able to train this so that when you show it an image that it has never seen before, it's likely to get it right. So, in fact, what's happening in a neural network like this is that it's building up features in a sort of hierarchical way, which is exactly what happens in the brain. Okay? There are some famous neuroscience experiments by Hubel and Wiesel that looked at the cat brains and the developing fetuses of cats, and showed that through different layers of the information processing circuits, the first layer was picking up, so actually your eyes are picking up different types of images, vertical lines with contrast, um, contrasts which are going sort of diagonally, maybe lines in the bottom right-hand corner of your visual field, maybe dark spots, maybe light spots. And you have all of these filters in your eye which pick up these different features, and they pass those back further into your brain, where the next layer might combine these in different ways to see, okay, we have something here which looks like an eye, and something here which looks like a nose, and something here which looks like a mouth. Okay? And then later on in the processing units in your brain, these combine again to give these sort of higher level, more abstract features. So these are very concrete features, more abstract features which correspond to, for instance, faces. So one might want to do something like pick out the sentiment, pick out the whether somebody is, for instance, happy or sad. And so you could train a neural network on images like this, where the output is maybe the emotional features on the person's face. And in doing so, the neural network will learn to pick up this hierarchy of features from very, very low level to much higher level, and can then have sort of a characteristic picture of a smiley face or a sad face or an angry, for instance. Okay. So we can just quickly go through sort of the history of what's happened since the perceptron. So we've got the perceptron that was invented in 1958 by Frank Rosenblatt. 1969, Minsky and Papert published this book, and unfortunately, this book did something rather unfortunate, which was to kind of give an idea that perceptrons, in the way that Frank Rosenblatt had put them together, weren't able to do all that much, that they were very limited. You know, they only had these sort of linear decision bounds. They do actually say in the book how one might get beyond that, but this caused what's called the first AI winter. So people had been very excited. You saw the quote from the New York Times about how the perceptron was going to give rise to self-replicating, talking, walking, conscious machines. And and Marvin Minsky and Seymour Papert came along and showed that, well, maybe we should, hold our horses. This, along with a report called the Lightfoot report, the Lighthill report, kind of put it put a bit of a halt on the development of AI. It really said, actually, the things that we thought were going to come about really couldn't come about. And in fact, Sir James Lighthill in his report said, in no part of the field have the discoveries made so far produced the major impact that was then promised. So this was 1972. And this really showed that, this report was from 1966, Computers and Translations and Linguistics. But the Lighthill report in 72 really said, actually, maybe this isn't quite as exciting as we thought. And we have the first AI winter. So a lot of research was pulled. A lot of the things that we were hoping would happen weren't able to happen. And people stopped doing research on things like neural networks. At least there was a lot less research than on neural networks. So 1972, Shinichi Amari comes along and says, actually, we can do something slightly different with these neural networks. So previously, we had sort of images of cats and dogs, and the output was maybe a number corresponding to the age of someone, or it was the classification of cat or dog. And Shinichi Amari said, well, when I have a sequence, let's say such a bad movie, and you hear me say those words, by the time I get to the word movie, you've already heard such a bad. And there is some memory, some short-term memory in your head of those words. They are connected in a really important sequential way. And it's important that each time you hear a new word, you are able to remember the previous words. So what Shinichi Amari did was to put in what's called a recurrent layer, which essentially takes the output. So I pass in the word such. It passes through that first layer, and then it comes back and is somehow aggregated with the word a. And then that goes through and is aggregated in some way with the word bad. And then the next word movie comes through and is aggregated. And so you end up forming what's called a hidden state in your brain, in the way that you have a memory of all of the words that have come before this, so that the next word in the sequence actually makes some sense. It's got some context. This is what's called a recurrent neural network. And really is the first way of understanding sequence data. So, up to now we've been able to understand images and maybe some very sort of basic types of data, but now we can understand sequence data, and this is really important. 1986, Geoffrey Hinton and others. So Geoffrey Hinton just won the Nobel Prize in Physics last year for his work on backpropagation. Yes, yeah, yeah. Along with Hopfield, also won the Nobel Prize in Physics last year. So what they were able to do was to say, how do we actually train this sort of neural network, this computational object? And they developed the so-called backpropagating errors, which essentially says each time you misclassify something, there is a very clear mathematical way to pass that information back through the network and update the weights, the connections, the strengths of the connection between them. 1989, Schmidhuber and others really took this idea of the visual cortex, the work of Hubel and Wiesel, and developed a way of analyzing images, which was much more powerful than just the simple multi-layer perceptron that we'd seen before. And this uses these ideas of the filters. And this is a so-called convolutional neural network. So around this time, we have the second AI winter. And the reason for that is that computational power wasn't enough that we could use these deep neural networks or these neural networks to perform the sorts of tasks that we really wanted to be able to do. So the types of things that we can do now, the computer power just wasn't there. So what people had been relying on was so-called expert systems. So in an expert system, imagine you want to program an electronic doctor. So one way you might do that would be lots of if-then statements. If the patient presents with this symptom, then that. If they have this and that, then this is what they have. If they come in presenting with this and their age is that, then et cetera, et cetera. So this is what's called an expert system. And essentially, it's a very complex set of rules. But they're rules that the human encodes themselves. They take all of their expertise and they try to encode it as a set of rules that the computer can then use to make these sorts of predictions. So there'd been sort of promised that these expert systems were going to be incredibly valuable in fields like medicine, in fields like predicting economic outcomes, these sorts of things. And it turned out that they just weren't powerful enough. So at this time, we didn't have enough computer power to really be able to utilize neural networks to do the exciting things that we wanted to be able to do. And at the same time, these expert systems hadn't really worked out. And so again, there was an enormous amount of funding pulled from the field for quite some time. 1997, Jürgen Schmidhuber again, who developed the convolutional neural network, said, okay, so the recurrent neural networks that we'd seen before that could deal with text, there's a problem with them. And the problem with them is that if you give it a really long piece of text, then it's really hard for it to remember what happened right at the beginning. So if I asked you to think about, what was the second word that I said during this presentation, it was a long, long time ago, and so you certainly wouldn't know. And indeed, each time I'm saying new words, you're sort of losing some information about what happened before. It's kind of being overwritten. I hope not completely overwritten, but you're more focused on the stuff that's happening right now. Schmidhuber comes along and sort of solves this problem to a large extent by saying, what's really important is not just remembering, but forgetting. So what he has is a sort of gating mechanism that when a new word comes in, there's something that says, this word is important. I need to encode this in my in the hidden state. Or actually, this word isn't really important. I can forget this. And as we go along, I can take bits out and say, that bit actually, I thought it was important, but it's not. And this is a so-called LSTM, or long short-term memory. So around the 2010s, something really important happens. And what this is, it's actually not about developing much more powerful types of neural networks. What's important is the data that is trained on. So Li Fei was the lead on this. And she said, what we really need is to come up with an enormous set of images, very well curated images. What happens if we try to train a neural network on millions and millions and millions of different images? And that's exactly what they did with so-called ImageNet. And it turned out that this was key. We were at a time by this point that computational power was enough that you could actually train these neural networks to make predictions. And when you do this on ImageNet, it turns out to be incredibly powerful. You pass in images, and it can classify them in a sort of hierarchical way as these are all mammals, these are placental mammals, carnivores, canines, dogs, working dogs, and it can actually tell you that these are Siberian Huskies and these are trimarans. And all that's going on here is, again, this sort of connection of neurons, these abstracted versions of neurons, and you're training them by passing in images, getting them to predict what the image is, and then propagating the error back through, because of course, when you give it a picture of a Siberian Husky to begin with, it has no idea what it is, but you then pass that error back through and just point it in the direction. You change the weights just a little bit so that next time it sees a Siberian Husky, it's more likely to give the correct prediction. Okay. So I think I'm not going to carry on with the next slide here because I want to go on to talk.
We've lost your sound.
Architecture came along, and it's called the transformer architecture. And it's a mechanism called attention. 2017, this paper comes along, and this is something really different. This is something very important because the way this new architecture works is that when you give it a sentence, it's able to understand the connection between words. Something that you have learned. Okay? You've learned something about the world. And so street, yes, that's something that can be described by it, but there's a much stronger signal here connecting animal with it. And what a transformer does is it learns to find these connections. And it turns out that that's very, very valuable. So ChatGPT comes along in around 2022. The way this works, so what I've been talking about is these neural networks making predictions. So let's say I give you a string of words. Let's say I give you the animal didn't cross the street because it was too tired. Okay. And I blank out the word tired. And all I do is I give you the word the animal didn't cross the street because it was too. Now I can ask you to make a prediction on it. I give you a sequence, the animal didn't cross the street because it was too, and you make a prediction. And maybe you make the prediction tired or dangerous or loud, whatever it might be. I then take that text and I say, well, you weren't quite right. Maybe you didn't say the word tired. You weren't right. Your prediction wasn't correct. But I move the weights in a way that you're more likely to get that word correct the next time. Okay? What that allows you to do is to develop a next word prediction neural network, which says that when I give you a string of words, you're going to predict what the next word in the sequence is. Okay? It was there in your head. You know what's coming next because your brain works as a next word prediction engine as well. ChatGPT has been trained with an enormous amount of data, huge amount of data, but that training, all it is doing, it's not a database of information. It's not a store of facts and figures and ideas about the world. It's In the same way that your brain is just a set of connections of neurons, what this is it is a model for predicting the next word in a sequence. And it turns out that that is far more powerful than we could ever have imagined. We didn't know that this was going to be able to take off in the way that it has. Because when you train something on next word prediction and you train it on essentially the entirety of the text which is on the web, it turns out that this can give you incredible things. So, we now know that ChatGPT and Claude and DeepSeek and all of these models, which are called transformers, transformer is the type of architecture, it turns out that they can do far, far more powerful things than we ever thought before. Beyond just writing poetry, we can now use them as researchers. So I use them on a daily basis to think about ideas. I might have some scientific idea and I want to kind of sense check it. I will put it into ChatGPT and I'll have a conversation with it, as I would do with a colleague. And I can say, do these two ideas seem to have some synergy between them? Yet all it is doing is next word prediction. That's at least what it seems. But somehow, in order to do next word prediction well, you need to have a model of the way the world works in your head. And that's what's happening with ChatGPT. There is a model in a very abstract form of the way the world works, which is encoded in the weights of the neural network in something like 1 trillion parameters, 1 trillion weights, so 1,000 billion weights or thereabouts. It has encoded an enormous amount of information about the world, not as a database, so you can't look it up. It's not like you can, so you can ask it questions and it appears to be looking it up, but it's not looking it up in the way that you would query a database. So I'm very happy to, go into all of the things that ChatGPT can do. We can give some examples of that, but I think I'm going to probably stop there and see if there are any questions at this stage. I'm sorry, I might have overwhelmed you with information.
I think all of us are either we're going to become brain surgeons or computer programmers after this.
Wonderful, wonderful.
Any questions, anybody? Yes, please. Please come up here and ask a question if you don't mind. Just talk here. There's a camera over there.
This may seem a really stupid question, but what happens to neural networks when this person decides to change their sex?
When the person decides to change their
sex?
The
gender.
Sure. So I guess the neural network itself. Do you mean the neural network in our brains or the neural network on the computer?
Sorry, I thought you were just answering the question. Yes, sorry.
Oh, do you mean the neural networks in our brain or the neural networks on a computer?
Well, the neural networks supposedly recognizing all these different bits and pieces to create an image. But the image is female, but now suddenly the image becomes male. How does that work?
Great. Yeah. So, if you're training, for instance, on images of men and images of women, then what it's going to do is to find general patterns. What it doesn't mean is that it has some sort of inherent insight into what's going on. All it's doing is, as a very crude example, it might figure out that long hair generally corresponds to people whose label are women, and that short hair generally corresponds to people whose label is men. Of course, it doesn't mean that, then so what that means then, if that's the classification that it's realized, and of course it would normally be more sophisticated than that, but then if a man comes along with long hair, it's going to predict that it's a woman because the feature it has found is the feature that it is associated with women. So all it's able to do is to take the various features and make generalization. Of course, if somebody looks like somebody who is not a stereotypical man or not a stereotypical woman, it's not going to be able to see what's going on in the brain to understand that unless you gave additional information. So, it's generically going to get, some people wrong because someone who might be a man who looks a bit more like the stereotypical woman and vice versa. So a system like this can certainly get those sorts of things wrong, but on average is likely to get them right.
Okay, so it's not 100% accurate.
Oh, absolutely not. In the same way that that humans are not 100% accurate. So if I gave you, for instance, handwritten digits, 0 to 9, and asked you to classify them, well, some people's handwriting isn't very good, and so maybe you wouldn't be able to classify them all as the person had hoped. So yeah, absolutely, such a system is not going to be 100% accurate unless there is a perfect distinction between the two classes.
Yeah, thanks.
Sure.
I'd like to ask a question. I have a general idea of how ChatGPT works because I've asked it a few questions like generate a list of all the birds that appear in the Western Cape, something like that.
Mm-hmm. Yeah.
It's sort of a set of data. But what fascinates me is we keep hearing reports that all different applications are going to be using AI in the future. So if a medical practice now wants to use AI, do they have to write special programs for the medical field, or do they use existing systems like ChatGPT to also answer medical questions?
Great. No, that's a brilliant question. So things like ChatGPT are very general. So they have been trained on a huge amount of data, and of course, some of that data is not correct. It might be that it's been trained on old textbooks, for instance. And so if you want to have something, for instance, which is specialized on medicine, what you would generally do is to train it to begin with very generally, and then train it again in a very specialized way just on the data that you want it to be to know more about. So what you do there is something called fine tuning. So it's very much equivalent to you have 18 years of growing up and schooling where you're learning general things about the world and understanding generally. But then you go to university and you're training on a very specific corpus, a very specific set of texts, which is the thing which is specialized, you're specialized on. And there you would create a separate ChatGPT for medicine, for instance. And so yeah, generically you'll have a separate system that you want to be just that much more accurate, that much more expert on a very particular area. So yeah, for each application, normally you're going to have something which is slightly different.
Now, this training, is that something that a person like myself could do, or do you need a special programmer to do that training?
Sure. So to do the training, so you do need to write Python code, for instance. So Python is one of the languages which is often used for this sort of thing. And so you do need to write code. You need to have a computer which is generally pretty powerful, where you download the weights, sort of the brain of the network. And then there's a particular training process to get it to learn on this new data by predicting sort of the next word in the sequence. There are actually systems that you can use to essentially push it in a direction of a particular set of knowledge. So in fact, for instance, with ChatGPT and with Claude, which is another model, what you can do is to upload a document and say, okay, with this document, I want you to make certain conclusions. Or you could upload a set of documents. And so you can give it particular information that you want it to work with. And so you can do that on just on the regular ChatGPT system. But that's not quite the same as the fine-tuning step, which is kind of that much more powerful. So often, for instance, if I want to understand a particular paper, the first thing that I'll do is that I'll upload it to Claude or ChatGPT and get it to explain kind of the general narrative. And then once I've got a general sense of it, then I go through myself in detail, working through it. So you can use it. So doing the fine tuning itself, that's something which does need a lot of programming, a lot of computer power. But you can get it to be sort of slightly more expert on particular systems for a given instance.
Where do they get all this information? I mean, do they take the books ever written in the world and get that information? Because I mean, ChatGPT took something like 12 years or whatever to develop. DeepSeek apparently took about 4 years. I mean, where were the sources of all the data that AI was in?
Were you able to pick that up?
So the question there was where did they get the data?
Where did they get all the data? Did they access
sure.
all books that have ever been written, or where was the data accessed?
Yeah, so yeah, I mean, this is a very important sort of ethical question. Lots of data has been taken from people who did not give consent for their data to be used for training such a model. But essentially, everything which is online and open to the public can be used, what was used and taken and used for the training. So, you know, if you've ever written a blog post which is out there in the public, or there's a book which can be found online, then all of that would have been used for the training. So it's what's called web scraping. So it essentially scrapes all of the information from the web and then uses that for the training. You know, there are very serious ethical implications about the, you know, the authors and artists whose work has been used for training a system like this. Yep.
Can it distinguish between fake news and actual data?
Oh, that's a great question. So part of the issue is that just in terms of a single article, the style of it, it's unlikely to be able to tell the difference. What one could think about doing would be to create a system which you can upload something and it can see if it can find verifiable sources for it. So now, because ChatGPT, for instance, you can ask it to look on the web. If you gave it an article and said, you know, is this fake news or not? It would be able to go out and say, well, I've actually found this on a reputable website or a number of reputable websites, and they, you know, it does seem to add up. Or, you know, there's some part of this story which doesn't seem to add up. So, as an example, I was reading a book a little while ago that I was very, very skeptical about, and I took some of the paragraphs and I put them into ChatGPT and I said, you know, can you verify this? And it was about a particular research paper, and it said, well, actually, you know, the research paper, it sort of says something a bit like that, but it's misrepresented this part. And so in that sense, if you ask it in the right way, it can, you know, of course, it's not infallible. You know, it will sometimes get these things wrong, and that you always have to keep that in mind whenever you're using a system like this. It is not infallible, but used in the right way, you can get it to help you to verify whether something is or is not fake news.
Hans? Can ChatGPT do what? Or can ChatGPT train itself?
So ChatGPT, in the way that it works at the moment, it needs a programmer to say, you know, essentially to write in, now use this data to train yourself. So the weights themselves, it is not able to alter them. But one could certainly think of a system which was able to do that. We don't really want that to happen at the moment because, you know, once the human is out of the loop, then we've lost control, and that may be extremely dangerous. So yeah, there's a lot of safety concerns about these sorts of systems because, you know, if it is able to train itself and we are not the ones that are controlling the training, then we don't know what's going to happen. I'm afraid I'm going to have to race off to a meeting in just one moment. Maybe one very quick question.
It's an extension of the previous question. What steps are required to give it its own sense of self-protection?
What steps are required to give it its own sense of self-protection?
Oh, can you repeat that? Sorry.
What are the next steps required for it to become self-aware?
Oh, to become self-aware. Oh, great question. Yeah, no, that's an extremely good question. I mean, I think if we understood that, we would probably also have to understand a lot about our own self-awareness. And there are questions there that we still don't understand. It's a really important question. You know, some people have said that these systems are self-aware. I'm not convinced, but I think it's a really important question and one that I'm very interested in as well. I'm afraid I'm going to have to run at this point. I have to race off to another meeting. If there are any more questions, please feel free to give people my email address, and they're welcome to write to ask me any questions.
Yes, you can forward any questions to me. Thank you very much.
Absolute pleasure. Thanks very much. Bye, everybody. Thanks.
Thank you, John.
Thanks.
Bye.